sklearn. Features election. Variance threshold. Description. A feature selection method that removes all features whose variance doesn't meet a certain threshold. It's a simple yet effective way to remove features that are constant or near constant, as they provide little to no information for the model. This technique is typically used as a preprocessing step before training more complex machine learning models. Inputs. X. A NumPy array or pandas data frame containing the features independent variables. Threshold. A float representing the minimum variance required for a feature to be retained. Features with a variance below this threshold will be removed. The default value is 0.0. Outputs. Transformed X. A NumPy array or pandas data frame containing only the features that met the variance threshold. Selected features. A list containing the indices of the features that were retained. Steps. Calculate the variance of each feature in the input data. Compare the variance of each feature to the provided threshold. Remove features whose variance is below the threshold. Metrics. Variance measures how much the values of a feature vary from its mean. Feature importance. Indirectly, a higher variance can suggest higher feature importance. Visualization plots. Histogram of feature variances. A histogram can visually display the distribution of variances across all features, allowing you to identify features with low variance. Fine-tune parameters. Threshold. This parameter directly controls which features are retained. Lowering the threshold will retain more features, while raising it will remove more features. It's important to experiment with different thresholds to find the optimal balance for your specific dataset. Uncertainty methods. Non-variance threshold is a deterministic method and doesn't inherently address uncertainty. However, the choice of the threshold itself can introduce uncertainty. Challenges and fixes. Challenge 1. Choosing the right threshold. Selecting a threshold that is too low might retain features that offer little predictive value, leading to overfitting. A threshold that is too high might remove valuable features, leading to underfitting. Sample use case that resulted in challenge 1. A dataset with a few features that have very low variance but are still predictive. Fixes to challenge 1. Experiment with different thresholds based on domain knowledge and the nature of the dataset. Utilize techniques like cross-validation to evaluate the performance of the model with different thresholds. Challenge 2. Feature scaling. Variance threshold is sensitive to the scale of the features. Features with larger scales will have higher variances, potentially leading to the removal of valuable features with smaller scales. Sample use case that resulted in challenge 2. A dataset where features have vastly different scales, e.g., one feature is in meters, another in kilograms. Fixes to challenge 2. Standardize or normalize the features before applying variance threshold. This ensures that all features have similar scales, preventing biases based on variance. Challenge 3. Handling correlated features. Variance threshold does not consider correlations between features. If two highly correlated features exist, variance threshold might remove one of them, even though both could be valuable for the model. Sample use case that resulted in challenge 3. A dataset with two features that have similar variance but are highly correlated. Fixes to challenge 3. Consider using feature selection methods that explicitly address correlations like select k-best with fclassif for classification or fregression for regression, or use feature engineering techniques to combine correlated features. sklearn features election chi2. Description. Explain in detail. The chi-squared test is a statistical test used to examine differences in categorical variables. In feature selection, it is used to assess the dependency between features and the target variable. The idea is to identify features that are statistically independent of the target, which are likely to be irrelevant for prediction. Inputs: X, a NumPy array or pandas data frame containing the features. Each row represents an instance, and each column represents a feature. Y, a NumPy array or pandas series containing the target variable. It should be a categorical variable. F score, a NumPy array containing the chi-squared statistics for each feature. Higher values indicate stronger dependence between the feature and the target. P-value, a NumPy array containing the p-values for each feature. Smaller p-values indicate that the feature is less likely to be independent of the target. Steps: calculate the observed frequencies for each feature and target value combination. Calculate the expected frequencies under the assumption of independence between the feature and the target. Compute the chi-squared statistic for each feature using the observed and expected frequencies. Calculate the p-value associated with each chi-squared statistic. Chi-squared statistic, a measure of the difference between observed and expected frequencies. Higher values indicate stronger dependence. P-value, the probability of observing the observed frequencies if the feature and the target were independent. Smaller p-values suggest dependence. Heat map of the chi-squared statistics, with features on one axis and target values on the other. Scatter plot of the chi-squared statistics against the p-values. None. The chi2 function does not have any tunable parameters. Confidence intervals for the chi-squared statistics. Bayesian methods to estimate the posterior distribution of the chi-squared statistics. Challenge 1: features with many categories can have inflated chi-squared statistics. Sample use case that resulted in challenge 1: a feature representing a user's location with many possible locations. Fixes to challenge 1: consider using feature engineering techniques to reduce the number of categories, or use a different feature selection method that is less sensitive to the number of categories. Challenge 2: features with low frequencies can have high p-values, even if there is a dependency with the target. Sample use case that resulted in challenge 2: a feature representing a rare disease with a small number of instances in the dataset. Fixes to challenge 2: consider using a different feature selection method that is less sensitive to low frequencies, or use techniques like oversampling or undersampling to balance the class distribution. sklearn, features election, fclassif. Description: the fclassif function calculates the ANOVA f value for each feature, assessing the separability between classes. It determins the statistical significance of each feature in differentiating between different classes. Inputs: X, a 2D array representing the feature matrix, where each row corresponds to an instance, and each column represents a feature. Y, a 1D array representing the target labels associated with the instances in X. Outputs: F, a 1D array containing the calculated F values for each feature. P, a 1D array containing the corresponding P values for each feature. Steps: calculate the ANOVA f statistic for each feature, measuring the variance between groups classes relative to the variance within groups. Compute the corresponding p-value for each feature, indicating the probability of observing the calculated f statistic if there were no real difference between the classes. Metrics: f-value. The f statistic measures the ratio of variance between groups to variance within groups. Higher f values suggest stronger evidence of class separation. P-value. The p-value quantifies the probability of observing the calculated F statistic under the null hypothesis of no class difference. Lower p-values indicate stronger evidence against the null hypothesis. Visualization plots. Feature importance plot. The F values can be visualized as a bar chart, showing the importance of each feature in classifying the data. Fine-tune parameters. None F class F does not have any fine-tuning parameters. Uncertainty methods. None F class F does not offer uncertainty quantification methods. Challenges and fixes. Challenge 1. High p-values may indicate that a feature is not significantly contributing to class separation. Sample use case. A feature might show very similar distributions across different classes, leading to a high p-value. Fixes. Consider removing features with high p-values. Investigate the reason for the high p-value to understand if it's due to noise or lack of real discriminatory power. Challenge 2. Features with low p-values may still not be useful for prediction if their effect is very small. Sample use case. A feature might show some statistical difference across classes but have a very weak relationship with the target variable. Fixes. Use feature importance measures, e.g., random forest feature importance, to assess the true predictive power of features. Examine feature interactions and correlations to understand how they might affect the observed p-values. sklearn. Features election. R regression. Description. This method ranks features by their correlation with the target variable using the Pearson correlation coefficient. Features with higher absolute correlation are considered more important. The resulting scores are then used to select the top-ranking features. Inputs. X a 2D array of features. Y a 1D array of target values. Outputs. Scores a 1D array of correlation scores for each feature. P-values a 1D array of p-values for each feature. Steps. Calculate the Pearson correlation coefficient between each feature and the target variable. Calculate the p-value associated with each correlation coefficient. Metrics. Correlation coefficient measures the strength of linear association between features and the target variable. P-value indicates the statistical significance of the correlation. Visualization plots. Correlation heat map shows the pairwise correlation between all features and the target variable. Feature importance plot ranks features based on their correlation scores. Fine-tune parameters. None. Uncertainty methods. Confidence intervals can be calculated for the correlation coefficients to estimate their uncertainty. Challenges and fixes. Challenge 1. High correlation between features can lead to multicollinearity, making it difficult to interpret the importance of individual features. Sample use case that resulted in challenge 1 using features that are highly correlated with each other, such as age and income. Fixes to challenge 1. Use feature selection techniques that handle multicollinearity, such as recursive feature elimination (RFE) or principal component analysis (PCA). Remove highly correlated features manually by inspecting the correlation matrix. Challenge 2. Correlation does not imply causation. A high correlation between a feature and the target variable does not necessarily mean that the feature is a causal factor. Sample use case that resulted in challenge 2 using a feature that is correlated with the target variable, but is not a direct causal factor. For example, ice cream sales and crime rates might be correlated, but neither causes the other. Fixes to challenge 2. Use domain knowledge to understand the causal relationships between features and the target variable. Consider using more sophisticated statistical models that account for confounding variables. sklearn, features election, mutual info class of. Description. This function calculates the mutual information between each feature and the target variable for classification problems. Mutual information is a measure of the dependency between two random variables. It quantifies how much knowing the value of one variable reduces uncertainty about the value of a other variable. In the context of feature selection, a higher mutual information value indicates that the feature is more informative for predicting a target variable. Inputs: X, a NumPy array or pandas data frame containing the features. Each row represents a sample, and each column represents a feature. Y, a NumPy array or pandas series containing the target variable labels. Outputs: mutual info, a NumPy array containing the mutual information scores for each feature. The index of the array corresponds to the column index of the features in X. Steps: calculate the empirical probability distribution of the features and target variable. Calculate the joint probability distribution of each feature and the target variable. Compute the mutual information for each feature using the formula mix, y sump x, y log 2 px, y px py. Metrics: mutual information, the core metric used, representing the dependency between features and the target variable. Visualization plots: feature importance plot, bar plot visualizing the mutual information scores of each feature, providing insights into the most informative features. Fine-tune parameters: discrete features, an array of booleans indicating whether each feature is discrete true or continuous false. This parameter is optional, and if not provided, the function will automatically determine the feature type based on the data. Challenges and fixes. Challenge 1: high cardinality categorical features can lead to inaccurate mutual information scores, as the function relies on empirical probability estimations, which can be unreliable with large numbers of categories. Sample use case that resulted in challenge 1: a dataset containing a categorical feature with hundreds of unique categories, resulting in a sparse probability distribution and unreliable mutual information estimations. Fixes to challenge 1: preprocess the categorical feature using techniques like one-hot encoding or label encoding to reduce the number of categories. Consider using alternative feature selection methods like chi-square test or ANOVA F test, which are more robust to high cardinality features. Challenge 2: imbalanced datasets can result in biased mutual information scores, as the function is sensitive to the distribution of the target variable. Sample use case that resulted in challenge 2: a dataset with a heavily skewed target variable distribution, e.g., 90 positive class, 10 negative class, potentially leading to misleading mutual information scores. Fixes to challenge 2: balance the dataset before applying mutual information-based feature selection. This can be achieved by techniques like oversampling the minority class, undersampling the majority class, or using synthetic data generation methods. Consider using alternative feature selection methods like recursive feature elimination (RFE) or feature importance scores from tree-based models, which are more robust to class imbalance. sklearn, features election, mutual infogression. Description: mutual information between two random variables is a measure of their statistical dependence. It quantifies how much knowing one variable reduces uncertainty about the other. In the context of feature selection, mutual information is used to estimate the relevance of features to a target variable. Specifically for regression tasks, the higher the between a feature and the target, the more informative that feature is for predicting the target. Inputs. X a 2D array of shape n samples. N features representing the features. Each row corresponds to a sample, and each column corresponds to a feature. Y a 1D array of shape n samples, representing the target variable. Outputs. Me a 1D array of shape n features, containing the estimated mutual information between each feature and the target variable. Steps. Calculate the empirical probability distribution of the features and the target variable using a non-parametric method, e.g., using histograms or kernel density estimation. Calculate the joint probability distribution of each feature and the target variable. Compute the mutual information for each feature using the formula mix YHX high, HX, Y, where HX is the entropy of feature X, high is the entropy of the target variable Y, and HX, Y is the joint entropy of X and Y. Metrics. Mutual information Me a measure of statistical dependence between features and the target variable. Higher Me indicates stronger relevance. Visualization plots. Bar chart visualizing the Me scores for each feature. Features with higher Me scores are more informative. Fine-tune parameters. Discrete features a Boolean array indicating whether each feature is discrete, true or continuous. False. This parameter is used to select the appropriate entropy estimator for discrete features. N neighbors, the number of neighbors to use for the k nearest neighbor estimator. This parameter is used for estimating the entropy of continuous features. Uncertainty methods. Bootstrapping repeatedly sample with replacement from the data to estimate the distribution of the Me scores and provide confidence intervals. Cross-validation. Split the data into multiple folds. Calculate the Me scores on each fold, and average the results. Challenges and fixes. Challenge 1. High-dimensional data can lead to overfitting and unstable Me estimates. Sample use case that resulted in challenge 1 using a dataset with hundreds of features and limited samples. Fixes to challenge 1. Feature dimensionality reduction techniques like principal component analysis (PCA) or feature selection methods based on other criteria, e.g., L1 regularization. Use ensemble methods like random forests to estimate the Me. Challenge 2. Discrete features with many categories can result in biased Me estimates. Sample use case that resulted in challenge 2. A dataset with a feature representing a categorical variable with thousands of unique values. Fixes to challenge 2. Binning group categories with similar values to reduce the number of unique categories. Discretization. Convert continuous features into discrete bins using methods like equal width or equal frequency binning. Challenge 3. Nonlinear relationships between features and the target variable might be missed by mutual information. Sample use case that resulted in challenge 3. A dataset where the relationship between a feature and the target is nonlinear, e.g., a quadratic relationship. Fixes to challenge 3. Apply feature transformations to capture nonlinear relationships, such as polynomial features, or use nonlinear models, e.g., support vector machines with a nonlinear kernel for regression. Challenge 4. Mutual information can be sensitive to outliers. Sample use case that resulted in challenge 4. A dataset with outliers in the features or target variable. Fixes to challenge 4. Preprocess the data to handle outliers, such as removing them or using robust estimation methods. Challenge 5. Computational cost can be high for large datasets, especially for calculating Me with high-dimensional features. Sample use case that resulted in challenge 5. A dataset with millions of samples and thousands of features. Fixes to challenge 5. Use approximate mean estimation methods that are more computationally efficient, such as the k-nearest neighbor estimator with a small number of neighbors. Utilize parallel computing techniques to distribute the mean calculation across multiple processes. Use feature selection methods based on other criteria, e.g., L1 regularization, that are more efficient than mean-based methods. sklearn feature extraction. Description: the feature extraction module in scikit-learn sklearn provides tools for extracting meaningful features from raw data, which is crucial for building effective machine learning models. These features can be numerical, categorical, or even text-based. The module offers methods for inputs, raw data. This could be text documents, images, numerical arrays, or any other data format suitable for feature extraction. Feature extraction method: the specific method used depends on the data type and the desired features. For example, for text data, one might use TF-IDF or count vectorizer. For images, feature extraction might involve extracting Hog features or using pre-trained deep learning models. Feature matrix: this is a numerical matrix where each row represents a data sample and each column represents a feature. Optional parameters depending on the chosen method. There might be additional outputs, such as vocabulary for text-based methods or feature weights for dimensionality reduction. Steps. Data preprocessing: this step involves preparing the raw data for feature extraction. It might include tasks like cleaning text data, scaling numerical features, or encoding categorical variables. Feature extraction: this is the core step where the chosen method is applied to extract the desired features. Feature transformation: optional in some cases. The extracted features might be further transformed for better performance. This could involve dimensionality reduction techniques like PCA or feature scaling. Metrics. Sparsity for text-based feature extraction. Sparsity measures how many of the extracted features are non-zero. This is important because sparse features can be more efficient to store and process. Feature importance: depending on the feature extraction method, it might be possible to calculate the importance of each extracted feature. This can help identify the most relevant features for a given task. Model performance: ultimately, the success of feature extraction is evaluated based on the performance of the machine learning model trained on the extracted features. Visualization plots. Feature importance plot: this plot can be used to visualize the importance of each extracted feature. Feature distribution plots: visualizing the distribution of features can help understand their characteristics and potential relationships. Dimensionality reduction plots: if dimensionality reduction is applied, plots can be used to visualize the transformed feature space. Maximum features: this parameter controls the number of features extracted. N-grams for text-based methods. This parameter specifies the length of the phrases considered during feature extraction. Vocabulary size for text-based methods. This parameter defines the size of the vocabulary used to represent words. Feature selection methods: techniques like L1 regularization, random forests, or feature importance scores can be used to select the most relevant features and reduce uncertainty. Ensemble methods: combining multiple feature extraction methods can help reduce uncertainty by averaging or voting on feature predictions. Challenge 1: overfitting. If the number of features extracted is too large compared to the number of training samples, the model might overfit to the training data. Sample use case that resulted in challenge 1: training a text classification model with a large vocabulary and a small training dataset. Fixes to challenge 1. Reduce the number of features by using feature selection methods or dimensionality reduction techniques. Increase the size of the training dataset. Challenge 2. Feature irrelevancy. Some extracted features might not be relevant to the task at hand, leading to noise and potentially degrading model performance. Sample use case that resulted in challenge 2. Extracting all words from a text corpus without considering their relevance to the classification task. Fixes to challenge 2. Use feature selection methods to identify and remove irrelevant features. Select a more appropriate feature extraction method that considers the specific task. Challenge 3. Curse of dimensionality. As the number of features increases, the distance between data points in the feature space can become very large, making it difficult to find meaningful patterns. Sample use case that resulted in challenge 3. Using a large number of features for image classification without applying dimensionality reduction. Fixes to challenge 3. Apply dimensionality reduction techniques like PCA or T-SNE to reduce the number of features while preserving important information. Use feature selection methods to identify and select the most relevant features. Challenge 4. Data imbalance. If the data is imbalanced, some features might be overrepresented in certain classes, leading to biased feature extraction. Sample use case that resulted in challenge 4. Extracting features from a dataset with a very small number of samples in one class compared to the other classes. Fixes to challenge 4. Use oversampling or undersampling techniques to balance the data before feature extraction. Use feature extraction methods that are robust to data imbalance. Challenge 5. Missing data. Missing values in the data can affect the feature extraction process, potentially leading to biased or inaccurate results. Sample use case that resulted in challenge 5. Extracting features from a dataset with missing values without performing imputation. Fixes to challenge 5. Impute missing values using appropriate methods like mean imputation, median imputation, or k-nearest neighbors imputation. Use feature extraction methods that are robust to missing data. sklearn. Feature extraction. Dict vectorizer. Description. The Dict vectorizer class in scikit-learn is a transformer that converts a list of dictionaries into a sparse matrix. It is used for representing categorical features as numeric values, which is necessary for many machine learning algorithms. Inputs. Input 1. A list of dictionaries. Each dictionary represents a sample, with keys representing the features and values representing the feature values. Input 2. A list of dictionaries where each dictionary represents a feature, with keys representing the feature names and values representing the feature values. Outputs. Output 1. A sparse matrix, where each row represents a sample and each column represents a feature. The values in the matrix indicate the presence or absence of a feature for a given sample. Output 2. A list of feature names, corresponding to the columns of the sparse matrix. Steps. Step 1. The Dict vectorizer first analyzes the input dictionaries to identify all unique features. Step 2. For each sample, the Dict vectorizer creates a vector with one element for each feature. The value of the element is 1 if the feature is present in the sample and 0 otherwise. Metrics. Metric 1. Sparsity. The percentage of 0 values in the sparse matrix. This metric indicates the efficiency of the representation. Visualization plots. Visualization plot 1. Heat map. A heat map of the sparse matrix can visualize the distribution of features across samples. Fine-tune parameters. Parameter 1. D-type. Data type of the output matrix. Parameter 2 sparse whether to return a sparse matrix or a dense matrix. Uncertainty methods. Uncertainty method 1 confidence intervals. The confidence intervals for the feature values can be estimated using bootstrapping or other methods. Challenges and fixes. Challenge 1 handling missing values if a feature is not present in a sample. The dict vectorizer will assign a 0 value to the corresponding element in the output vector. This can lead to misleading results if the missing values are not truly 0. Sample use case that resulted in challenge 1 a dataset with features representing the presence or absence of specific medical symptoms, where missing values indicate that the symptom was not recorded. Fixes to challenge 1. Use a separate flag variable to indicate missing values, and treat them differently from 0 values. Challenge 2 handling high cardinality features if a feature has a very large number of unique values. The dict vectorizer can create a very large sparse matrix, leading to memory issues and computational inefficiency. Sample use case that resulted in challenge 2 a dataset with a feature representing the text of a customer review, where each unique text could be considered a distinct value. Fixes to challenge 2. Use feature hashing or dimensionality reduction techniques to reduce the number of unique values. sklearn. Feature extraction. Feature hasher. Description. The feature hasher class is a powerful tool in scikit-learn for transforming categorical features into numerical features, particularly when dealing with high cardinality datasets or situations where the number of unique categories is unknown or potentially very large. It leverages the concept of hashing to map categorical features to unique integer indices. This process often results in a sparse representation, where most entries are 0, which is memory efficient. Inputs. Input 1 input data. This should be a list of lists. Each inner list represents a single sample, a NumPy array, or a pandas data frame. Each element of the input should represent a categorical feature. Input 2 n features, an integer specifying the number of features to be generated. This parameter controls the size of the hash space, and therefore the potential for hash collisions. Outputs. Output 1 transformed data, a sparse matrix, typically a SCPI, sparse, CSR matrix containing transformed numerical features. Each row represents a sample, and each column corresponds to a unique hash value feature. Output 2 feature names. If the input type is string, the feature names are generated as X followed by the hash value. Steps. Step 1 feature hashing. The algorithm maps each categorical feature to a unique integer index using a hash function. The hash function ensures that similar features are likely to have similar hash values, helping to preserve some of the original information. Step 2 sparse matrix creation. The hashed features are used to construct the sparse matrix where non-zero entries correspond to the hashed feature values. This sparse matrix represents the transformed data. Metrics. Metric 1 sparsity. The sparsity of the resulting matrix, which is the percentage of 0 values, can be a good indicator of the effectiveness of the hashing process. Metric 2 hash collisions. While the hash function is designed to minimize collisions, it's important to consider the possibility of features mapping to the same hash value. The extent of collisions can impact the accuracy of the model. Visualization plots. Visualization plot 1 sparsity plot. A visualization depicting the distribution of non-zero entries in the sparse matrix can help understand the level of sparsity. Visualization plot 2 hash collision distribution. A plot illustrating the distribution of hash Values and the frequency of collisions can provide insights into the performance of the hash function. Fine-tune parameters. Parameter 1 n features. Determining the right value for n features is crucial. Too small a value can lead to an excessive number of collisions, while too large a value can result in a sparse matrix with many unnecessary features. Parameter 2 input type. The input type parameter specifies how the input features are interpreted. It can be set to string for raw strings, pair for pairs of strings useful for representing relationships between entities, or dict for dictionaries. Choosing the appropriate input type is vital for accurate transformation. Uncertainty methods. Uncertainty method 1 ensemble hashing, employing multiple feature hashes with different hash functions and combining their outputs can help mitigate the impact of hash collisions and improve the robustness of the feature transformation. Challenges and fixes. Challenge 1 hash collisions. Sample use case that resulted in challenge 1 when dealing with high cardinality data. The potential for hash collisions increases. This can lead to features being incorrectly grouped together, impacting model accuracy. Fixes to challenge 1. Increase n features. Expanding the hash space by increasing n features reduces the probability of collisions. Ensemble hashing. Using multiple hashes with different functions can help mitigate collisions. Challenge 2 feature importance interpretation. Sample use case that resulted in challenge 2 interpreting feature importance after feature hashing can be challenging, as the generated features are essentially hash values. Fixes to challenge 2. Feature importance analysis. Using feature importance techniques that consider the sparsity of the transformed data and the distribution of hash values can provide meaningful insights. Combining with other techniques. Integrate feature hasher with other feature engineering methods to enhance interpretability. sklearn feature extraction. Image feature extraction from images using scikit-learn. sklearn involves converting raw image data into a set of meaningful features that can be used by machine learning models. These features capture essential information about the image, such as color, texture, shape, and spatial relationships between different parts of the image. Sklearn provides various tools for feature extraction from images, enabling effective representation of visual data for tasks like image classification, object detection, and image retrieval. Inputs. Input 1 explain in detail image data. This could be a single image or a collection of images. Images can be loaded from different formats, such as JPG, PNG, or TIFF, using libraries like OpenCV or PIL. Input 2 explain in detail preprocessing steps. Image data may require preprocessing before feature extraction. This can include steps like resizing, normalization, and color space conversion to prepare the images for analysis. Output 1 explain in detail feature vectors. The extracted features are typically represented as numerical vectors, where each element corresponds to a specific feature. The dimensionality of these vectors can vary depending on the chosen feature extraction method. Output 2 explain in detail feature matrix. When processing multiple images, the extracted feature vectors are organized into a feature matrix, where each row represents the feature vector of a single image. Steps. Step 1 explain in detail image loading. Images are loaded from their source using appropriate libraries and converted into a suitable format for analysis, often as a multi-dimensional array representing pixel values. Step 2 explain in detail feature extraction. Sklearn provides a variety of feature extraction methods for images, including color histogram. Summarizes the distribution of colors in the image, capturing overall color content. Texture descriptors capture the arrangement of pixels and patterns, such as homogeneity, smoothness, and contrast. Shape descriptors describe the geometric properties of objects within the image, such as area, perimeter, and aspect ratio. Local binary patterns (LBP) detect local intensity changes and create patterns that represent texture variations. Hogg histogram of oriented gradients capture edge and shape information by quantifying pay. Distribution of gradient directions. Metrics. Metric 1 explain in detail feature extraction performance. Evaluate the effectiveness of pay. Extracted features in terms of how well they distinguish between different classes or capture relevant information for downstream tasks. Metric 2 explain in detail computational efficiency. Consider the time and computational resources required to extract features. This is particularly important for large datasets or real-time applications. Visualization plots. Visualization plot 1 explain in detail feature distribution plots. Visualize the distribution of extracted features to understand their range, variability, and potential correlation. This can be done using histograms, scatter plots, or other appropriate plotting techniques. Visualization plot 2 explain in detail feature importance analysis. Use methods like feature selection or permutation importance to identify the most informative features, providing insights into which features contribute the most to the performance of the model. Parameter 1 explain in detail number of bins. Adjust the number of bins in histogram-based methods to control the level of granularity in feature representation. Parameter 2 explain in detail window size in methods like LBP. The window size determines the local region used for feature extraction. Uncertainty method 1 explain in detail ensemble methods. Use multiple feature extraction techniques or different parameter settings for each technique to create an ensemble of feature representations. This helps capture a wider range of information and reduces the impact of individual feature extraction biases. Uncertainty method 2 explain in detail Bayesian approaches incorporate prior knowledge or probabilistic models to estimate the uncertainty associated with extracted features, providing confidence intervals or probability distributions for feature values. Challenge 1 explain in detail high dimensionality feature extraction methods often produce a large number of features, which can lead to the curse of dimensionality, making it difficult to learn accurate models and increasing computational complexity. When using Hogg features for object detection, the high dimensionality can lead to overfitting and poor generalization performance, especially when training on limited data. Dimensionality reduction techniques apply techniques like principal component analysis (PCA) or linear discriminant analysis (LDA) to reduce the dimensionality of feature space while preserving important information. Feature selection use methods like feature importance analysis or regularized regression to identify and select the most informative features, discarding irrelevant or redundant ones. Challenge 2 explain in detail computational cost. Some feature extraction methods, like Hogg or deep learning-based approaches, can be computationally expensive, particularly when processing large images or datasets. Real-time image classification applications require efficient feature extraction to ensure timely processing, especially on devices with limited computational resources. Fixes to challenge 2. Optimized implementations utilize libraries like OpenCV or scikit-image that provide optimized implementations of feature extraction algorithms for speed and efficiency. Parallelization leverage multi-core processors or GPUs to parallelize the computation of feature extraction, reducing overall processing time. Feature caching store pre-computed features for frequently used images, reducing the need for repeated extraction. sklearn, feature extraction, image, extract patches 2D. Description. This function extracts patches of a given size from an image, either from a single image or a batch of images. Each patch is a contiguous block of pixels within the original image. Inputs. Image a 2D or 3D array representing the image or a batch of images. The last two dimensions correspond to image height and width, respectively. Patch size a tuple of two integers per chait. Patch width specifying the size of each extracted patch. Outputs. Patches a 4D array containing the extracted patches. The shape of the output is n patches per chait. Patch width. N channels, where n patches is the total number of patches extracted. Indices a 2D array with shape n patches. 2 containing the coordinates row, column of each extracted patch in the original image. Steps. The function iterates over the image, sliding a window of size patch size over the image. For each window position, a patch is extracted and stored in the output array. The indices of each extracted patch are also stored in the output array. Metrics. None. Visualization plots. None. Fine-tune parameters. Patch size controls the size of the extracted patches. Smaller patch sizes extract more fine-grained features, while larger patch sizes capture broader context. Extraction step determines the step size of the sliding window. A larger step size leads to fewer extracted patches, while a smaller step size extracts more patches, potentially capturing more features. Uncertainty methods. None. Challenges and fixes. Challenge 1. When extracting patches from the edge of an image, the patch might extend beyond the image boundaries. Sample use case that resulted in challenge 1 attempting to extract patches of size 5 from an image with dimensions 10 using a sliding window with a step size of 1. Fixes to challenge 1. Set the parameter extract border to true to allow the extraction of patches that extend beyond the image boundaries. Challenge 2. Extracting patches from a very large image can be computationally expensive and memory intensive. Sample use case that resulted in challenge 2. Extracting patches from a high-resolution image, e.g. 10,000 by 10,000 pixels with a patch size of 100. Fixes to challenge 2. Consider using techniques such as patch sampling or subsampling to reduce the number of patches extracted. sklearn, feature extraction, image, gridograph. Description. This function converts a grid of pixel values into a graph representation where each node represents a pixel and edges connect neighboring pixels. This graph representation can be used for various image analysis tasks like segmentation, edge detection, and texture analysis. Image a 2D NumPy array representing the image. Each element in the array represents a pixel value. Mask a 2D NumPy array representing a mask that specifies which pixels should be included in the graph. Pixels with non-zero values in the mask are included. If none, all pixels are included. Return only edges if true. Only the edges of the graph are returned. If false, the nodes and edges are returned. Graph a SciPy sparse matrix representing the graph. Each row and column of the matrix corresponds to a pixel. The value at I J is 1 if there is an edge between pixel I and pixel j. Otherwise 0. Nodes are NumPy array of shape n nodes, representing the node labels. This is only returned if return only edges is false. Iterate over the pixels in the image and create a node for each pixel. Connect each pixel to its neighboring pixels based on the specified connectivity 4 connectivity or 8 connectivity. Return the graph, either as a sparse matrix edges only or as a tuple of nodes and edges. Number of nodes, the number of pixels in the image that are included in the graph. Number of edges, the number of connections between pixels in the graph. Graph density, the ratio of edges to the maximum possible number of edges in the graph. Graph visualization, the graph can be visualized using graph plotting libraries like NetworkX or Matplotlib. Mask, by specifying a mask, you can select specific regions of interest in the image and exclude other pixels from the graph. This can be useful for focusing on specific features in the image. Return only edges, this parameter controls whether the function returns only the edges of the graph or the nodes and edges. This can be useful if you are only interested in the connections between pixels. None, this method doesn't have any specific uncertainty methods. Challenge 1 for very large images. The graph can become too large and dense to process efficiently. Sample use case that resulted in challenge 1, trying to analyze a high-resolution satellite image. Fixes to challenge 1. Subsampling, you can reduce the size of the graph by subsampling the image. This involves selecting a subset of pixels to include in the graph. Graph simplification, you can simplify the graph by removing unnecessary edges. For example, you could remove edges that connect pixels with similar values. Challenge 2, the graph can be highly connected, making it difficult to analyze and extract meaningful information. Sample use case that resulted in challenge 2, analyzing an image with a lot of texture or detail. Fixes to challenge 2. Thresholding, you can use thresholding to remove edges that connect pixels with small value differences. This can help to reduce the density of the graph. Graph clustering, you can cluster the nodes in the graph based on their connectivity and similarity. This can help to identify different regions in the image. sklearn, feature extraction, image, inctograph. Description, the inctograph function converts an image into a graph representation. The image is first divided into a grid of patches, with each patch representing a node in the graph. The edges between nodes are determined by the similarity between the patches, measured using a chosen similarity metric. This graph representation can then be used for various image analysis tasks, such as image segmentation, object recognition, and image retrieval. Inputs. Image, the input image to be converted into a graph representation. The image can be in any format supported by scikit-image, such as a NumPy array or a file path. Mask, a binary mask that specifies the regions of the image to be included in the graph. This parameter is optional, and if not provided, the entire image will be used. Return as the format in which the graph is to be returned. This can be either adjacency matrix or sparsegraph. The adjacency matrix is a dense representation of the graph, while the sparse graph representation is more memory efficient. Metric, the metric to be used for computing the similarity between patches. This can be any metric supported by scikit-learn, such as Euclidean, Manhattan, or cosine. Radius, the radius of the neighborhood to be considered when computing the similarity between patches. This parameter determines how many neighbors each node will have in the graph. Outputs. Graph, the output graph representation of the input image. The format of the graph depends on the returner's parameter. Steps. Divide the input image into a grid of patches. Calculate the similarity between each pair of patches using the chosen metric. Construct the graph by connecting nodes patches based on their similarity. Metrics. The quality of the graph representation can be assessed by its ability to capture the important features of the image. For example, a good graph representation should be able to segment the image into meaningful regions or identify objects of interest. Visualization plots. The graph representation can be visualized by plotting the nodes and edges, with the thickness of the edges representing the strength of the connections between nodes. Visualization tools such as NetworkX can be utilized to generate visualizations for the image. Graph. Fine-tune parameters. The radius parameter controls the density of the graph. A larger radius results in a denser graph with more connections between nodes. The metric parameter influences the similarity measure used to connect nodes. Choosing an appropriate metric is crucial for accurate graph construction. Uncertainty methods. The uncertainty in the graph representation can be estimated by examining the distribution of similarity scores between patches. Patches with low similarity scores are more likely to represent uncertain boundaries in the image. Challenges and fixes. Challenge 1. The choice of the metric can significantly impact the graph representation. Sample use case that resulted in challenge 1 using the Euclidean distance metric for images with different color distributions may lead to inaccurate similarity measurements and an incorrect graph representation. Fixes to challenge 1. Experiment with different metrics, such as cosine distance, to find the best metric for the specific image type and task. Challenge 2. The radius parameter can influence the density of the graph, which may affect the performance of downstream tasks. Sample use case that resulted in challenge 2 using a large radius for an image with fine details might result in a very dense graph, making it difficult to identify important features. Fixes to challenge 2. Adjust the radius parameter based on the size and complexity of the image to create a graph that is appropriate for the task at hand. sklearn. Feature extraction. Image. Reconstruct from patches 2D. Description. This function reconstructs an image from a collection of 2D patches. It effectively stitches together the patches to form the original image, taking into account the overlap between patches. Inputs. Patches. A 4-dimensional array of shape n patches. Patch height. Patch width. N channels representing the individual patches. Each patch is a 2D array with the specified height, width, and number of channels. Patch shape. A tuple. Patch height. Patch width specifying the dimensions of each patch. This should match the shape of the individual patches in the patches array. Outputs. Image. A 3-dimensional array of shape. Image height. Image width. N channels representing the reconstructed image. This image is formed by arranging the patches in the correct order and handling overlaps. Steps. Patch arrangement. The function arranges the patches in a grid-like structure based on the overlap defined by the patch shape and the input patches. Overlap handling. The overlapping regions between adjacent patches are handled by averaging pay values from the overlapping pixels. This ensures a smooth transition between patches. Visualization plots. Original image vs. reconstructed image. A side-by-side comparison of the original image and the image reconstructed from patches can visualize the effectiveness of the reconstruction process. Fine-tune parameters. Patch shape. The size of the patches used for reconstruction. Larger patches might lead to faster reconstruction but could also introduce blurring. Challenges and fixes. Challenge 1. Incomplete patch coverage. If the input patches do not completely cover the entire Image. The reconstruction might result in missing regions or artifacts. Sample use case that resulted in challenge 1: reconstructing an image with a patch size that is too small to capture the entire image. Fixes to challenge 1: ensure that the input patches completely cover the entire image by either using a larger patch size or by providing enough patches. Challenge 2: poor patch overlap if the overlap between patches is insufficient. The reconstructed image might exhibit visible seams or discontinuities. Sample use case that resulted in challenge 2: using a patch shape where the overlap is too small to effectively smooth out transitions between patches. Fixes to challenge 2: increase the overlap between patches by adjusting the patch shape or using a larger patch size. Challenge 3: image shape mismatch if the patch shape and the original image shape are not compatible. The reconstruction might result in an incorrect image size. Sample use case that resulted in challenge 3: using a patch shape that does not divide evenly into the image dimensions. Fixes to challenge 3: ensure that the patch shape is compatible with the original image shape by padding the image or adjusting the patch shape accordingly. sklearn. Feature extraction. Image. Patch extractor. Description: the patch extractor class in scikit-learn's image feature extraction module extracts patches of a specific size from an input image. These patches can then be used as features for machine learning models, particularly in tasks like image classification or object detection. Inputs. Image: a 2D or 3D NumPy array representing the input image. The shape of the array should be height. Width for grayscale images or height. Width. Channels for color images. Patch size: a tuple specifying the desired width and height of the extracted patches. For example, 8. 8 would extract 8 by 8 pixel patches. Outputs. Patches: a NumPy array containing the extracted patches. The shape of the array will be number of patches. Patch size 0. Patch size 1 for grayscale images or number of patches. Patch size 0. Patch size 1. Channels for color images. Steps. Initialization: the patch extractor object is initialized with the desired patch size. Extraction: the extract method is called on the input image to extract patches. The extraction process typically involves sliding a window of the specified patch size across the image, extracting a patch at each position. Metrics. Patch coverage measures the proportion of the input image covered by extracted patches. Visualization plots. Patch visualization visualizes the extracted patches, potentially showing their spatial arrangement within the original image. Fine-tune parameters. Patch size controls the size of the extracted patches, influencing the level of detail captured. Extraction step specifies the step size used to slide the patch window across the image. A smaller step size results in more overlapping patches. Uncertainty methods. Patch variance calculates the variance of pixel values within each extracted patch to estimate patch uncertainty. Challenges and fixes. Challenge 1: boundary handling: when the patch window reaches the edge of the image, it may extend beyond the image bounds. Sample use case that resulted in challenge 1: extracting 10 by 10 patches from a 100 by 100 image might result in patches that partially extend outside the image boundary. Fixes to challenge 1: the patch extractor class offers options for boundary handling, including padding the image with zeros or mirroring the image content. Challenge 2: computational cost: extracting patches from large images can be computationally expensive. Sample use case that resulted in challenge 2: extracting 100 by 100 patches from a high-resolution image, like a satellite image, can consume significant processing time. Fixes to challenge to consider using parallel processing techniques or optimizing the patch extraction algorithm for faster execution. sklearn feature extraction text description. The sklearn feature extraction text module provides tools for converting text data into numerical representations that can be used for machine learning models. This is a crucial step in natural language processing (NLP) because most machine learning algorithms require numerical inputs. This module offers a range of techniques for text feature extraction, including bag of words. BO represents text as a vector where each element corresponds to the frequency of a word in the text. Term frequency inverse document frequency TF-IDF weights words based on their frequency within a document and their rarity across the entire corpus. Hashing vectorizer maps words to integer indices without storing a vocabulary, making it memory efficient. Count vectorizer counts word occurrences in text documents. Inputs. Text data. The input is text data, which can be a list of strings, a corpus of documents, or a single string. Preprocessing options. You can specify various preprocessing steps, such as lowercase conversion, stop word removal, stemming, lemmatization, and tokenization. Outputs. Numerical feature matrix. The output is a numerical feature matrix, where each row represents a text document and each column corresponds to a feature. The values in the matrix represent the frequency or importance of each feature in the corresponding document. Vocabulary. Some methods like count vectorizer and TF-IDF vectorizer provide a vocabulary which is a mapping between words and their corresponding indices in the feature matrix. Steps. Tokenization. Text is broken down into individual words or phrases called tokens. Normalization. Text is transformed into a standard format, e.g., converting to lowercase, removing punctuation, or stemming words. Feature extraction. Features are extracted from the processed text based on the chosen method BO. TF-IDF. Hashing. etc. Metrics. Accuracy. A metric commonly used for classification tasks to evaluate the model's performance. Precision measures the proportion of correctly classified positive samples among all predicted positive samples. Recall measures the proportion of correctly classified positive samples among all actual positive samples. F1 score. The harmonic mean of precision and recall, providing a balanced measure of performance. AUC area under the curve evaluates the performance of binary classification models by considering the trade-off between precision and recall. Mean squared error MSE used for regression tasks to measure the average squared difference between predicted and actual values. Visualization plots. Word clouds visualize the most frequent words in a text corpus. Heat maps illustrate the relationships between features and their importance in the dataset. Scatter plots used for visualizing the relationships between features and the target variable. Fine-tune parameters. Max features. The maximum number of features to be extracted. NGRAM range. The range of n-grams to be considered unigrams, bigrams, trigrams, etc. Stop words. A list of words to be removed from the text. MinDF. The minimum document frequency for a word to be considered. MaxDF. The maximum document frequency for a word to be considered. Uncertainty methods. Confidence intervals can be used to estimate the uncertainty of the model's predictions. Bayesian inference provides a framework for quantifying uncertainty in model parameters. Challenges and fixes. Challenge 1. High dimensionality. BO and TF-IDF can create very high dimensional feature spaces. leading to computational challenges and potential overfitting. Sample use case: a large corpus of text with a diverse vocabulary could result in a feature matrix with millions of columns. Fixes: feature selection: use techniques like feature importance ranking, L1 regularization, or dimensionality reduction (PCA), SVD to select the most relevant features. Hashing vectorizer reduces the dimensionality by using a hash function to map words to a fixed size feature space. Challenge 2: sparse data. Text data often results in sparse feature matrices, where most values are 0. Sample use case: a document containing only a few words from a large vocabulary will have a sparse feature vector with mostly zeros. Fixes: sparse matrix representation: use libraries like SciPy's sparse matrices to efficiently store and process sparse data. Sparse matrix operations use algorithms specifically designed for sparse data, such as L1 regularization or sparse PCA. Challenge 3: handling rare words. Bow and TF-IDF can give high weights to rare words, which might not be informative. Sample use case: a word appearing only in a few documents can have a high TF-IDF score, even if it's not semantically meaningful. Fixes: smoothing techniques: use techniques like Laplace smoothing or add-one smoothing to prevent rare words from dominating the feature space. Word embedding: use word embedding models like Word2Vec or GloVe to capture semantic relationships between words and represent them as dense vectors. Challenge 4: handling out of vocabulary OOV words. New words not present in the training vocabulary can't be processed. Sample use case: when a model encounters a word it has never seen before, it cannot assign a feature vector to it. Fixes: unknown word token: assign a special token for unknown words and treat them as a separate feature. Subword tokenization: break words into smaller units, subwords, to handle words not seen during training. Word embedding: use pre-trained word embedding models that cover a vast vocabulary. Challenge 5: handling different text lengths. Documents with different lengths can lead to biases in the feature space. Sample use case: a short document with high word frequencies might be misclassified compared to a long document with the same words but lower frequencies. Fixes: normalization by document length: divide word counts by the document length to account for variations in text lengths. Sentence embedding: use sentence embedding techniques to represent entire sentences as fixed length vectors, regardless of their lengths. Truncation and padding: truncate longer documents and pad shorter ones to ensure all documents have the same length. sklearn, feature extraction, text, count vectorizer. Description: explain in detail. Count vectorizer is a powerful tool for converting text data into a numerical representation suitable for machine learning algorithms. It counts the occurrences of each unique word or token in a corpus of documents, generating a sparse matrix where each row represents a document and each column corresponds to a unique word. This process is crucial for enabling machine learning models to analyze and understand text data. Inputs. Input 1: explain in detail a list of strings representing the text data. Each string corresponds to a document in the corpus. Input 2: explain in detail optional parameters to fine-tune the vectorizer's behavior, such as vocabulary size, stop words removal, and tokenization settings. Outputs. Output 1: explain in detail a sparse matrix typically in CSR format where each row represents a document, and each column corresponds to a unique word. The values in the matrix represent the frequency of each word in each document. Output 2. Explain in detail a vocabulary dictionary mapping words to their corresponding column. Indices in the output sparse matrix. Steps. Step 1. Explain in detail. The text data is split into individual words tokens using the specified tokenizer. Step 2. Explain in detail. The unique words across all documents are identified to form a vocabulary. Step 3. Explain in detail. The occurrence of each word in each document is counted, and the counts are stored in a sparse matrix. Metrics. Metric 1. Explain in detail. Vocabulary size. Number of unique words can indicate the complexity of the text data. Metric 2. Explain in detail. Document sparsity. Percentage of zero values in the sparse matrix can indicate the diversity of words used in each document. Visualization plots. Visualization plot 1. Explain in detail. Word clouds can be used to visualize the most frequent words in the corpus. Visualization plot 2. Explain in detail. Heat maps can be used to visualize the distribution of words across documents. Fine-tune parameters. Parameter 1. Explain in detail. Vocabulary. A predefined vocabulary of words to use for vectorization. This can be useful for ensuring consistency across different datasets. Parameter 2. Explain in detail. Stop words. A list of words to be ignored during vectorization. Commonly used stop words include articles, prepositions, and conjunctions. Parameter 3. Explain in detail. NGRAM range. The range of n-grams to be considered during vectorization. Unigrams. Single words are the default, but bigrams, pairs of words, or trigrams, triples of words can be used to capture more context. Parameter 4. Explain in detail. Max features. The maximum number of features unique words to be considered. This parameter can be used to reduce dimensionality and improve computational efficiency. Uncertainty methods. Uncertainty method 1. Explain in detail. None. As count vectorizer itself doesn't inherently model uncertainty. However, subsequent models that use the vectorized output might have their own uncertainty measures. Challenges and fixes. Challenge 1. Explain in detail. Handling rare words. Words that appear only a few times in a corpus might not be informative for machine learning models. Sample use case that resulted in challenge 1. A dataset containing product reviews might have a few unique words specific to a particular product that only appear once or twice. Fixes to challenge 1. Use MindDef parameter to ignore words appearing less than a certain threshold. Use MaxDef parameter to ignore words appearing more than a certain threshold. Challenge 2. Explain in detail. Large vocabulary size. A very large vocabulary can lead to high dimensionality and computational challenges. Sample use case that resulted in challenge 2. A corpus of news articles might contain tens of thousands of unique words. Fixes to challenge 2. Use max features parameter to limit the vocabulary size. Use dimensionality reduction techniques like principal component analysis (PCA) or latent semantic analysis (LSA) after vectorization. Challenge 3. Explain in detail. Handling different word forms. Words with different inflections, e.g., run, running, ran, might be treated as distinct words, leading to information loss. Sample use case that resulted in challenge 3. A dataset containing tweets might have variations in word forms. Fixes to challenge 3. Use a stemming or lemmatization technique before vectorization to reduce words to their base forms. Use the lowercase parameter to convert all words to lowercase, reducing the impact of capitalization differences. Challenge 4. Explain in detail. Handling out of vocabulary words. Words not present in a training vocabulary will be ignored during prediction. Sample use case that resulted in challenge 4. A sentiment analysis model trained on product reviews might encounter new product names during prediction. Fixes to challenge 4. Use the unknown token parameter to handle unseen words. Consider using a technique like hashing or word embedding to represent words outside the vocabulary. sklearn, feature extraction, text, hashing vectorizer. Description. Hashing vectorizer is a feature extraction technique used in natural language processing (NLP) to convert text data into numerical vectors that can be used in machine learning models. It utilizes hashing to map words to indices in a fixed-length vector, making it efficient for large datasets and memory-constrained scenarios. Inputs. Text data corpus. This can be a list of strings, each representing a document or text sample. Optional parameters. N features specifies the number of features hash buckets to use. Norm controls the normalization method for feature vectors. Alternate sign if true. Uses alternate signs in hashing to reduce collisions. NGRAM range defines the range of n-grams to consider, e.g. unigrams. Bigrams. Outputs. Feature matrix. A sparse matrix where each row represents a document and each column corresponds to a hashed feature word. Vocabulary in hashing vectorizer. There is no explicit vocabulary maintained. Steps. Tokenization. The input text is split into individual words or tokens, e.g. using whitespace or punctuation as delimiters. Hashing. Each token is hashed using a hash function to generate a unique integer index within a specified n features. Vector representation. A sparse vector is created for each document, where the value at each index corresponding to a hashed feature represents the frequency of that feature in the document. Metrics. Accuracy measures the model's performance on a classification or regression task. Precision indicates the proportion of correctly predicted positive instances. Recall represents the proportion of actual positive instances that were correctly identified. F1 score. A harmonic mean of precision and recall, providing a balanced evaluation metric. Visualization plots. Feature importance plots visualize the importance of different features hashed words in a model's predictions. Confusion matrices display the distribution of correctly and incorrectly classified instances for multi-class problems. Word clouds create visual representations of the most frequent words in the corpus. Fine-tune parameters. N features experiment with different values to control the number of features and potentially affect model performance. Norm. Consider different normalization methods L1, L2, none based on the specific machine learning algorithm being used. NGRAM range. Adjust the range of n-grams to capture different semantic relationships, e.g. unigrams, bigrams, trigrams. Uncertainty methods. Bayesian optimization. Optimize hyperparameters using probabilistic methods to find the optimal combination for the model. Cross-validation. Evaluate model performance with different data splits to assess its generalization ability. Challenges and fixes. Challenge 1. Hash collisions due to the fixed size feature space. Collisions can occur where multiple distinct words hash to the same index, leading to information loss. Sample use case that resulted in challenge 1. When dealing with a large vocabulary or a limited number of features, collisions are more likely to occur. Fixes to challenge 1. Increase n features. Using a larger feature space can reduce the likelihood of collisions. Choose a robust hash function. Employ hash functions with good distribution properties to minimize collisions. Challenge 2. Loss of word order information. Hashing vectorizer treats words as independent units. disregarding the order in which they appear in the text. Sample use case that resulted in challenge to models that rely on word order, such as recurrent neural networks, may perform poorly when using hashing vectorizer. Fixes to challenge 2. Use n-grams. Incorporate n-gram sequences of words into the feature representation to capture some word order information. Consider alternative techniques for tasks that require word order. Explore techniques like word embeddings or TF-IDF that preserve positional information. sklearn, feature extraction, text, TF-IDF transformer. Description: the TF-IDF transformer is a class in scikit-learn that transforms a count matrix of words into a matrix of TF-IDF features. TF-IDF stands for term frequency, inverse document frequency. It is a common technique in text mining and information retrieval used to weight words based on their importance within a document and across a corpus. Inputs: term frequency matrix, TF matrix. This is a matrix where each row represents a document and each column represents a word in the vocabulary. The values in the matrix represent the number of times a specific word appears in a document. Vocabulary: this is a list of unique words that appear in the entire corpus of documents. Outputs: TF-IDF matrix. This is the transformed matrix, where each row represents a document and each column represents a word in the vocabulary. The values in this matrix are the TF-IDF scores of each word in each document. Steps: term frequency. TF calculation calculates the frequency of each word in a document. This is simply the count of the word divided by the total number of words in the document. Inverse document frequency. IDF calculation calculates the inverse document frequency of each word in the corpus. IDF measures the rarity of a word across the entire collection of documents. It is calculated as the logarithm of the total number of documents divided by the number of documents containing the word. TF-IDF calculation multiplies the TF score by the IDF score for each word in each document to obtain the TF-IDF score. This score represents the importance of a word in a document, taking into account both its frequency within the document and its rarity across the corpus. Metrics: precision, the proportion of retrieved documents that are relevant. Recall, the proportion of relevant documents that are retrieved. F1 score, the harmonic mean of precision and recall. Visualization plots. Heat map, a visualization of the TF-IDF matrix, where the color intensity represents the TF-IDF score. Word cloud, a visual representation of the most important words in a document or corpus, where the size of each word is proportional to its TF-IDF score. Fine-tune parameters. Norm L1, L2, none. Default L2. L1 normalizes each document to have unit L1 norm. L2 normalizes each document to have unit L2 norm. None, no normalization is performed. USE-IDF Boolean. Default true. True, use inverse document frequency IDF. False, do not use IDF. Smooth IDF Boolean. Default true. True, smooth IDF weights by adding 1 to document frequencies, as if an extra document was seen containing every term in the corpus. This prevents zero division errors. False, no smoothing is performed. Subline ARTF Boolean. Default false. True, applies sublinear TF scaling, i.e. replace TF with 1 log_TF. False, no sublinear TF scaling is performed. Uncertainty methods. Confidence interval measures the uncertainty in the TF-IDF scores by calculating the confidence interval around the mean. Challenges and fixes. Challenge 1: Data sparsity. When dealing with a large corpus, the TF-IDF matrix can become extremely sparse, with many zero values. This can lead to computational issues and affect the performance of downstream tasks. Sample use case that resulted in Challenge 1: A corpus of news articles with millions of documents can result in a very sparse TF-IDF matrix. Fixes to Challenge 1: Dimensionality reduction techniques. Methods like principal component analysis (PCA) or singular value decomposition (SVD) can be used to reduce the dimensionality of the TF-IDF matrix by identifying the most important features. Feature selection. Only keep the most informative features based on criteria like information gain or chi-squared statistics. Challenge 2: Overfitting. If the training data is not sufficiently representative of the real world data, the TF-IDF model can overfit the training data, leading to poor generalization performance on unseen data. Sample use case that resulted in Challenge 2: A training dataset consisting of only technical documents may not be representative of a broader range of text data. Fixes to Challenge 2: Regularization techniques. Techniques like L1 or L2 regularization can help prevent overfitting by penalizing large weights in the model. Cross-validation. Divide the data into training, validation, and testing sets to evaluate the model's performance on unseen data and adjust the model accordingly. sklearn, feature extraction, text, TF-IDF vectorizer. Description: A transformer that converts a collection of text documents to a matrix of TF-IDF features. TF-IDF stands for term frequency, inverse document frequency. It is a numerical statistic that reflects how important a word is to a document in a collection of documents. Inputs: raw documents, a list of strings, each representing a document. Vocabulary: an optional list of words to consider. If provided, only these words will be used to build the vocabulary. Outputs: TF-IDF matrix, a sparse matrix of TF-IDF features, where each row represents a document and each column represents a word in the vocabulary. Vocabulary: a dictionary mapping words to their corresponding column indices in the TF-IDF matrix. Steps: tokenization: the input text is split into individual words tokens. Vocabulary building: a vocabulary of unique words is created from the entire corpus of documents. Term frequency calculation: for each document, the frequency of each word in the vocabulary is counted. Inverse document frequency calculation: the inverse document frequency IDF of each word is calculated based on its frequency across all documents. This measures how rare a word is. TF-IDF calculation: the term frequency TF of each word in each document is multiplied by its IDF to produce the TF-IDF score. Metrics: non-TF-IDF is not a metric, but rather a feature representation. Visualization plots: non-visualization is not typically done directly on the TF-IDF matrix, but rather on the results of models using it as input. Fine-tune parameters: NGRAM range controls the size of word sequences n-grams to consider. MaxDF ignores words that occur in more than a specified percentage of documents. MindDF ignores words that occur in less than a specified percentage of documents. Max features limits the vocabulary to a maximum number of features. USE-IDF whether to use IDF weighing true by default. SmoothIDF whether to smooth IDF weights true by default. Uncertainty methods: non-TF-IDF is a deterministic transformation, not a probabilistic one, so uncertainty methods are not applicable. Challenges and fixes: Challenge 1 out of vocabulary OOV words. Words that are not present in the original vocabulary are ignored. Sample use case that resulted in challenge 1: a document containing a new word not seen during training. Fixes to challenge 1: use a larger corpus for training. Consider using a word embedding model like Word2 Vec or BLOV. Use a vocabulary expansion method such as stemming or lemmatization. Challenge 2: sparse matrix representation. The TF-IDF matrix is often sparse, meaning most values are 0. This can impact efficiency for some algorithms. Sample use case that resulted in challenge 2: performing linear algebra operations on the sparse matrix. Fixes to challenge 2: use efficient sparse matrix libraries like SciPy, sparse. Consider using dimensionality reduction techniques like principal component analysis PCA to reduce sparsity. Challenge 3: overfitting to rare words. TF-IDF can give high weights to words that appear rarely, but are specific to a few documents. This can lead to overfitting. Sample use case that resulted in challenge 3: building a text classification model where some rare words are highly predictive of a specific class. Fixes to challenge 3: use techniques like regularization or feature selection to control the influence of rare words. Consider using alternative feature representations like word embeddings that capture semantic relationships between words. sklearn features election. Description: feature selection is a crucial step in machine learning that involves selecting a subset of relevant features from the original dataset. This helps in reducing the dimensionality of the data, improving model performance, and simplifying the model. It is especially beneficial when dealing with datasets containing a large number of features, many of which may be irrelevant or redundant. Feature selection can be broadly categorized into two types: filter methods, which select features based on their intrinsic characteristics, and wrapper methods, which evaluate features based on the performance of the chosen model. Inputs: data: a dataset containing the features and target variable. This can be a pandas data frame or a NumPy array. Target variable: the column in the dataset that represents the outcome or the variable to be predicted by the model. This can be a categorical or numerical variable. Outputs: selected features: the subset of features that have been chosen by the feature selection method. This can be a list of feature names or indices. Model: optionally, the selected features can be used to train a machine learning model, which can then be used for prediction or classification. Steps: feature ranking: assign a score or rank to each feature based on its relevance to the target variable. Feature selection: select the top-ranked features based on a predefined threshold or criterion. This can be done using various methods like univariate feature selection, recursive feature elimination RFE, or feature importance scores from tree-based models. Metrics: feature importance score: a measure of how relevant each feature is to the prediction task. Higher scores indicate more relevant features. Accuracy: the proportion of correctly classified instances, often used to evaluate the performance of the model after feature selection. F1 score: a harmonic mean of precision and recall, useful for evaluating the performance of models on imbalanced datasets. Area under the curve: AUC: a measure of the overall performance of the model, especially for binary classification problems. Visualization plots: feature importance plot visualizes the importance scores of each feature, allowing for easy identification of the most relevant features. Correlation matrix plot shows the correlation between different features, which can help identify redundant features. Fine-tune parameters: Threshold: the minimum score or rank required for a feature to be selected. Number of features: the desired number of features to be selected. Often set based on the desired level of dimensionality reduction. Feature selection method: the specific algorithm or technique used for feature selection, such as univariate feature selection, RFE, or feature importance from tree-based models. Uncertainty methods: bootstrapping, resampling the data multiple times to estimate the variability in feature selection results. Cross-validation, evaluating the performance of the model with selected features on different subsets of the data to assess the model's robustness. Challenges and fixes. Challenge 1: overfitting to the training data, leading to poor generalization on unseen data. Sample use case that resulted in challenge 1: selecting too many features based on their performance on the training set, potentially including features that are specific to the training data and do not generalize well. Fixes to challenge 1: use cross-validation to evaluate the model's performance on unseen data and select the features that perform well across multiple folds. Employ regularization techniques like L1 or L2 regularization during model training to prevent overfitting. Challenge 2: selecting features that are not truly relevant or are redundant. Sample use case that resulted in challenge 2: selecting features that are highly correlated with each other, leading to redundancy and potential overfitting. Fixes to challenge 2: examine the correlation matrix of features to identify and remove highly correlated features. Use feature selection methods that explicitly account for feature dependencies, such as recursive feature elimination (RFE). Challenge 3: missing values in the data, leading to inaccurate feature selection results. Sample use case that resulted in challenge 3: univariate feature selection methods might not perform well with missing values. Fixes to challenge 3: impute missing values using appropriate methods before performing feature selection. Use feature selection methods that are robust to missing values, such as methods based on tree-based models that naturally handle missing data. sklearn, feature selection, generic univariate select. Description: generic univariate select is a method transformer for feature selection that applies a univariate feature selection to each feature. It takes a score function and a strategy, e.g., percentile, k-best, to select the best features based on the score. Inputs: scoring. This is a callable function that evaluates the univariate feature selection. It should take two arguments, the training data x and the target variable y, and return a tuple of two arrays, the scores and the p-values. Examples of score functions include fclassif for classification tasks and fregression for regression tasks. Param: this is a parameter controlling the selection strategy. It can be a dictionary with parameters for the specific selection strategy or a single parameter. Value mode: the mode of the feature selection. There are two modes, percentile and k-best. Percentile: this mode selects features based on the percentile of the scores. It takes a parameter called percentile that specifies the percentile to use. K-best: this mode selects the top k features based on the scores. It takes a parameter called k that specifies the number of features to select. Outputs: transform X new, the transformed feature matrix where only the selected features are retained. Selected features: a list of the indices of the features that were selected. Steps: 1. Fit the estimator using the input data and target variable. 2. Calculate the scores and p-values for each feature using the specified score function. 3. Apply the selection strategy to the scores to determine the features to keep. 4. Return the transformed feature matrix where only the selected features are retained. Metrics. F-score, a common metric for evaluating feature selection. Accuracy, the percentage of correctly classified instances. Visualization plots. Feature importance plot. This plot shows the importance of each feature based on the scores. Correlation matrix. This plot visualizes the correlations between features, helping identify features that may be redundant. Fine-tune parameters. Percentile, the percentile of features to select using the percentile mode. K, the number of features to select using the K-best mode. Uncertainty methods. Bootstrap resampling, repeatedly sampling with replacement from the data and evaluating feature. Importance. Cross-validation, splitting the data into folds. Training the model on one fold and evaluating on another. And calculating feature importance for each fold. Challenges and fixes. Challenge 1. Overfitting. The model may be overfitting to the training data, leading to poor performance on unseen data. Sample use case, selecting features based on a small training set with high variance in feature scores. Fixes to challenge 1. Use cross-validation to evaluate the model's performance on unseen data. Use a regularization technique, such as L1 or L2 regularization, to prevent overfitting. Increase the size of the training data. Challenge 2. Multicollinearity. When features are highly correlated, it can be difficult to determine which features are most important. Sample use case, selecting features in a dataset where multiple features are highly correlated with each other. Fixes to challenge 2. Use feature selection techniques that are robust to multicollinearity, such as lasso regularization. Perform principal component analysis (PCA) to reduce the dimensionality of the data. Carefully consider the domain knowledge and select features based on their relevance to the task. sklearn. Features election. Select percentile. Description. Select percentile is a feature selection method in scikit-learn sklearn that ranks features based on a scoring function and selects the top percentile of features. This method is useful for reducing the dimensionality of data by keeping only the most relevant features. Inputs. Scoffing, a function that takes two arguments, the training data X and the target labels Y, and returns a score for each feature. This function defines the criteria for feature ranking. Common scoring functions include fclassif, ANOVA f-value for classification tasks. This measures the variance between class means divided by the variance within classes. Mutual info, classif, mutual information for classification tasks. This quantifies the dependency between features and the target variable. Chi2, chi-squared statistic for classification tasks. This assesses the independence between categorical features and the target variable. Fregression, ANOVA f-value for regression tasks. This measures the variance between group means divided by the variance within groups. Mutual infogression, mutual information for regression tasks. This quantifies the dependency between features and the target variable. Percentile, the percentile of features to select. For example, if percentile 50, then the top 50 of features based on the scores will be selected. Outputs. Transformed data, the transformed dataset with only the selected features. This output will have a reduced number of columns compared to the original data. Selected features, a list or array of indices representing the features that were selected. Steps. Scoring the scoring is applied to the input data X and target labels Y. Generating a score for each feature. Ranking the features are ranked based on their scores. The top features based on the percentile value are selected. Transformation: the input data X is transformed by keeping only the selected features. Metrics. Feature importance scores: the scores generated by the scoring provide a measure of feature importance. Model performance: the performance of a machine learning model trained on the transformed data can be used to assess the effectiveness of feature selection. Visualization plots. Feature importance plots: a bar chart or histogram can visualize the importance scores of features. This can help identify the most important features for the prediction task. Scatter plots. Scatter plots can visualize the relationship between the selected features and target variable. Fine-tune parameters. Scoring: choosing the appropriate scoring function is crucial for effective feature selection. The choice of scoring function depends on the type of task classification, regression, and the nature of the features. Percentile: the percentile value determines how many features are selected. A higher percentile selects more features, potentially leading to better performance but also higher dimensionality. Uncertainty methods. Cross-validation: using cross-validation to evaluate the model's performance with different feature subsets can help estimate the robustness of the selected features. Challenges and fixes. Challenge 1: choosing the correct scoring function for the specific task and data. Sample use case: using the F-class scoring function for a regression task. Fixes: using the appropriate scoring function based on the type of task, e.g. regression for regression or exploring different scoring functions. Challenge 2: setting the percentile parameter appropriately to balance feature selection and model performance. Sample use case: selecting a very low percentile, leading to the exclusion of potentially important features. Fixes: experimenting with different percentile values through cross-validation to find a balance between feature selection and model performance. sklearn. Features election. Select K-best. Description. Select K-best is a feature selection technique in scikit-learn sklearn that helps you identify and retain the top K features from a dataset based on their scores from a chosen scoring function. Inputs. X. This is your input dataset, usually represented as a NumPy array or a pandas data frame. Each row represents a data point sample, and each column corresponds to a feature. Y. This is the target variable dependent variable for your supervised learning problem. It's a NumPy array or pandas series containing labels or values corresponding to the data points in X. Scoring. This is the function used to evaluate the importance of each feature. Sklearn offers various built-in score functions, such as F-class for classification problems and regression for regression problems. Mutual info class of mutual infogression. Cheat 2. Select percentile. You can also supply a custom function if you have a specific feature scoring method in mind. K. The number of top features you want to select. Outputs. Transform. The output is a transformed version of your input data X containing only the selected K features. The dimensionality of the data is reduced. Scores. This attribute provides the scores for each feature according to the chosen score function. This can be useful for understanding the relative importance of features. Steps. Feature scoring. The chosen score function scoring is applied to each feature in your dataset X, evaluating its relationship with the target variable Y. The score reflects the feature's ability to predict or explain the target variable. Feature ranking: the scores are then ranked, allowing you to identify the features with the highest scores. Feature selection: the top K features with the highest scores are selected based on the value of K provided. Metrics: feature importance: the scores provided in the scores attribute can be used to assess the relative importance of the selected features. Features with higher scores are considered more important. Model performance: after applying Select K Best, you'll typically use the transformed data with a machine learning model. You can evaluate the model's performance on the selected features to assess if feature selection improved accuracy or efficiency. Visualization plots: feature importance plot: you can create a bar chart or a heat map to visualize the feature scores. This helps you understand which features are most important. Fine-tune parameters. K: this is a crucial parameter controlling the number of features to select. Experimenting with different K values can be useful to find a balance between model performance and complexity. Scoring: selecting the right score function for your problem is essential. If your data is categorical, for example, you might consider Chi2 or Mutual Info Classif instead of F Classif. Challenges and fixes. Challenge 1: overfitting. If K is too large, Select K Best might include noisy or irrelevant features, leading to overfitting. Sample use case: in a text classification problem with a lot of words, using a very high K value might include words that are specific to a few training examples but not generalizable to new data. Fixes: reduce K, try smaller K values to select fewer features. Cross-validation: use cross-validation techniques to assess if your model is generalizing well. Regularization: incorporate regularization techniques, e.g., L1 or L2 regularization into your model to penalize complex models and prevent overfitting. Challenge 2: choosing the right score function. Using a score function that doesn't align with your data or task can lead to suboptimal feature selection. Sample use case: using regression for a categorical target variable might not be appropriate because it's designed for continuous targets. Fixes: data understanding: thoroughly understand the nature of your data and the task at hand to choose a score function that aligns with the problem domain. Experimentation: try different score functions and compare their performance on your data. Domain knowledge: if possible, incorporate domain knowledge to guide your selection of the scoring function. sklearn. Features election. Select FPR. Description. Select features according to a p-value threshold using F-test for feature scoring. This technique is used to select features with p-values below a certain threshold, effectively keeping features that are statistically significant based on the F statistic. Inputs. X, the input feature matrix of shape n samples. N features. Y, the target vector of shape n samples. Outputs. Support a Boolean mask of shape n features, with true values indicating selected features. Ranking an array of shape n features. Of feature ranks, with the most important feature assigned rank 1. Steps. Feature selection. Calculate the F statistic for each feature, which measures the variance explained by the feature. P-value thresholding. Compute the p-value for each feature based on the F statistic. The features with p-values below the specified threshold are selected. Metrics. F statistic, a measure of how much variance in the target variable is explained by each feature. P-value, the probability of observing the F statistic if there is no relationship between the feature and the target variable. Visualization plots. Feature importance plot a bar chart showing the F statistic for each feature. Sorted by importance. Feature selection plot a plot showing the number of selected features as a function of p-value threshold. Fine-tune parameters. Alpha the p-value threshold. Features with p-values below alpha are selected. Uncertainty methods. Bootstrapping resample the data with replacement to estimate the variability of the feature. Selection process. Challenges and fixes. Challenge 1 overfitting if the threshold is set too low. It can lead to overfitting, where the model performs well on the training data but poorly on unseen data. Sample use case that resulted in challenge 1 when using a low alpha value, e.g. 0.01 on a dataset with a high number of features. The model may select many features that are only weakly related to the target variable. This can result in a model that is overfitted to the training data and performs poorly on unseen data. Fixes to challenge 1 use cross-validation to estimate the performance of the model on unseen data. Consider using a higher alpha value to reduce the number of selected features. Challenge 2 multicollinearity if the features are highly correlated. The F-test may not accurately reflect the importance of individual features. Sample use case that resulted in challenge 2 when dealing with datasets containing features that are strongly correlated, e.g., multiple measures of the same concept. The F-test might select features that are only weakly related to the target variable due to the correlation with other features. Fixes to challenge 2 consider using techniques like principal component analysis (PCA) or other dimensionality reduction methods to address multicollinearity. Alternatively, apply feature selection methods that are robust to multicollinearity, such as lasso regression. sklearn. Features election. Select F-doctor. Description. Select features according to a p-value threshold using F-classif for classification or for regression. For regression, this feature selection algorithm is based on the false discovery rate (FDR) approach. It controls the expected proportion of falsely rejected null hypotheses features that are not informative. It uses the Benjamini-Hochberg procedure to correct for multiple comparisons. Inputs. X the training input samples. This should be a 2D array, where each row represents a sample and each column represents a feature. Y the target values. This can be a 1D array for regression or a 1D array of class labels for classification. Outputs. Selected features returns a Boolean mask of shape n features, where true indicates that the corresponding feature should be selected. Transformed data the data with only the selected features. Steps. Calculate the p-values for each feature using F-classif or for regression. Depending on the task, apply the Benjamini-Hochberg procedure to adjust the p-values for multiple comparisons. Select features with a p-value below the specified alpha threshold. Metrics. Accuracy the proportion of correctly classified samples. Precision the proportion of true positives among all predicted positives. Recall the proportion of true positives among all actual positives. F1 score the harmonic mean of precision and recall. R squared for regression. The proportion of variance explained by the model. Mean squared error MSE for regression. The average squared difference between predicted and actual values. Visualization plots. Feature importance plot a bar chart showing the importance of each feature. Scatter plots for regression tasks. Scatter plots can be used to visualize the relationship between the features and the target variable. Confusion matrix for classification tasks. A confusion matrix can be used to visualize the performance of the model on each class. Receiver operating characteristic ROC curve for binary classification tasks. An ROC curve can be used to visualize the trade-off between true positive rate and false positive rate. Fine-tune parameters. Alpha, the false discovery rate threshold. This determines the expected proportion of falsely rejected null hypotheses. The default value is 0.05. Uncertainty methods. Bootstrapping sampling with replacement to estimate the variability of the feature selection process. Cross-validation, evaluating the model on multiple folds of the data to estimate its generalization performance. Challenges and fixes. Challenge 1, features with low variance may not be selected even if they are informative. Sample use case that resulted in challenge 1, a dataset with features that have very similar values across all samples may lead to a low variance. Fixes to challenge 1. Standardize the features to ensure that all features have the same variance. Consider using a different feature selection method that is less sensitive to variance. Challenge 2, the number of features selected can vary depending on the dataset and the alpha threshold. Sample use case that resulted in challenge 2, datasets with a large number of features may lead to the selection of many features, even with a low alpha threshold. Fixes to challenge 2. Adjust the alpha threshold to control the number of features selected. Consider using other feature selection methods to reduce the number of features selected. sklearn features election, select from model. Description. Select from model is a feature selection method that uses a machine learning model to evaluate the importance of each feature. It selects the features that are most important according to the model, discarding the rest. This is a wrapper-style feature selection method, as it relies on a model to score each feature. You can use it to select features that contribute the most to the prediction. Inputs. Estimator, an instance of a machine learning model that has a feature importances or core attribute. This attribute reflects the importance of each feature for the model's predictions. The estimator must be trained on the data. Threshold. This parameter determines the selection criteria. It can be a string, median, mean, auto, a float value, or a function that returns a threshold. Outputs. Support a Boolean array indicating which features are selected. True for selected features, false for discarded features. Transform. This method transforms the input data by selecting only the features that were identified as important. Steps. Train the estimator. Train the chosen machine learning model on the training data. Feature importance evaluation. The model will assign an importance score to each feature based on its contribution to the model's predictions. Feature selection based on the threshold specified. Features are selected. The threshold can be set as a specific value or a percentile like median or mean, or auto, which calculates the threshold based on the distribution of feature importance scores. Metrics. Feature importance scores. The importance scores assigned to each feature by the trained estimator. Visualization plots. Feature importance plot. Visualizing the feature importance scores using a bar chart or a heat map can help identify the most influential features. Fine-tune parameters. Threshold. This parameter determines the selection criteria. By setting a higher threshold, you'll select fewer features and vice versa. Uncertainty methods. Bootstrap aggregation. You can train multiple models with different subsets of the data to estimate the variability of feature importance scores. Cross-validation. Use cross-validation to evaluate the performance of the model with different sets of selected features. Challenges and fixes. Challenge 1. Overfitting to the training data. If the model overfits the training data, It might assign high importance to features that are not truly informative. Sample use case: a model trained on a dataset with many noisy features might assign high importance to some of these features due to random correlations. Fixes: regularization techniques like L1 and L2 regularization can help prevent overfitting by penalizing large weights. Feature scaling: scaling features to a common range can improve the model's performance and reduce the impact of features with different scales. Cross-validation: use cross-validation to evaluate the model's performance on unseen data and identify overfitting issues. Challenge 2: feature redundancy. The selected features might be highly correlated, meaning that they provide similar information. Sample use case: selecting features like temperature in Celsius and temperature in Fahrenheit will result in redundant features. Fixes: feature correlation analysis before using select from model. Analyze the correlation between features using methods like Pearson correlation or Spearman's rank correlation. Remove highly correlated features. Feature selection techniques: explore other feature selection methods like recursive feature elimination RFE or select k-best that handle feature redundancy. sklearn. Features election. Select FWE. Description. Select FWE is a feature selection method that uses a f-test to rank features by their statistical significance. It then selects the features whose p-values are below a user-specified threshold using the f-test. The f-test measures the variance between the means of two groups divided by the variance within each group. This method is useful for selecting features that are most likely to be predictive of the target variable, while also controlling the family-wise error rate FWER at a given level. Inputs. Scoffing: a function that takes two arrays x, y and returns a pair scores. P-values, where scores is a 1D array of scores for each feature and p-values is a 1D array of corresponding p-values. Alpha: the alpha level for the f-test, corresponding to the desired family-wise error rate FWER. A higher alpha means a higher chance of selecting irrelevant features. Outputs. Selected features: a Boolean array of the same length as the number of features. True indicates that the feature is selected. False indicates it is not selected. Features ranking: a 1D array of feature indices, sorted in decreasing order of f-statistic. Steps. Calculate the f-statistic and p-value for each feature using the input scoffing. Rank the features in decreasing order of the f-statistic. Use the specified alpha level to determine the p-value threshold. Select all features with p-values below the threshold. Metrics. F-statistic measures the variance between the means of two groups divided by the variance within each group. Higher values indicate more significant features. P-value represents the probability of observing the given data if there is no relationship between the feature and the target variable. Lower values suggest a stronger association. Visualization plots. Feature importance plot. This plot can be created using the feature ranking and f-statistics to visualize the relative importance of each feature. Feature selection heat map. This can be used to visualize the correlation between features and a target variable, with different colors representing the strength of correlation. Fine-tune parameters. Scoffing: adjust the score function based on the type of data and the relationship you are looking for, e.g., using ANOVA for categorical target or a regression model for continuous target. Alpha: increasing alpha allows for more features to be selected, but increases the chance of false positives. Uncertainty methods. Permutation testing. This can be used to assess the stability of the feature selection results by randomly shuffling the target variable and rerunning the feature selection process. Bootstrap aggregating can be used to estimate the uncertainty of the feature selection process. By resampling the data with replacement and repeating the feature selection process multiple times. Challenges and fixes. Challenge 1: Overfitting due to choosing too many features. Sample use case: using a very low alpha value, e.g., 0.01 for a dataset with a large number of features. Selecting many features that may not be truly important, and leading to overfitting. Fixes: increase the alpha value to reduce the number of features selected. Use cross-validation to assess the performance of the model with different numbers of selected features. Apply regularization techniques to the model to prevent overfitting. Challenge 2: Underfitting due to choosing too few features. Sample use case: using a very high alpha value, e.g., 0.5 for a dataset with a small number of features. Selecting too few features to capture the underlying relationships, and leading to underfitting. Fixes: decrease the alpha value to increase the number of features selected. Explore using other feature selection methods that are less restrictive, such as select k-best, a recursive feature elimination. Consider adding more features to the dataset. Challenge 3: Selecting features that are highly correlated with each other. Sample use case: using select FWE on a dataset with multiple features that are highly correlated with each other. The method may select only one of the correlated features while discarding the others, leading to an incomplete representation of the underlying relationships. Fixes: use a different feature selection method that explicitly considers feature correlations, such as select from model with AL1 penalty. Apply dimensionality reduction techniques, such as PCA, to reduce the number of features while preserving the most important information. Manually analyze the correlated features and select only a subset that is most relevant. Challenge 4: Selecting features that are not relevant to the target variable. Sample use case: when the dataset contains features that are correlated with the target variable, but are not truly causal. This can happen if there is a confounding variable that affects both the feature and the target. Fixes: conduct domain-specific analysis to identify and remove irrelevant features. Use causal inference techniques to identify features that have a causal relationship with a target variable. Employ feature selection methods that consider the causal relationships between features and a target variable. sklearn, features election, sequential feature selector. Description: sequential feature selector is a feature selection method that iteratively adds or removes features based on a specified scoring function. It can be used for both feature selection and dimensionality reduction. There are two main variants: forward selection, which starts with an empty set of features and adds one feature at a time, and backward elimination, which starts with all features and removes one feature at a time. Inputs: estimator, the machine learning model to use for feature scoring. This can be any estimator that has a fit method and a score method or predict proba for classification tasks. N features to select the number of features to select. If auto, the number of features will be determined by the scoring function. Direction, the direction of feature selection. It can be forward add features or backward remove features. Scoring, the scoring function to use. This can be a string-like accuracy, F1, ROCOC, or a custom scoring function. CV, the cross-validation strategy to use. This can be an integer number of folds, a CV object, or none. Use the default CV strategy of the estimator. Outputs: Support a Boolean array indicating which features were selected. Ranking an array containing the ranking of each feature 1 is the best. Steps. Initialization. The feature selection process starts with either an empty set of features for forward selection or with all features for backward selection. Feature evaluation. For each iteration, the algorithm evaluates the performance of the estimator with the current set of features using the specified scoring function and cross-validation. Feature selection. Based on the performance evaluation, the algorithm selects the feature that leads to the best improvement, forward selection or removal. Backward selection. In the score iteration, the process repeats until the desired number of features is selected. Metrics. Scoring metric used for feature evaluation. Examples include accuracy, precision, recall, F1 score, AUC, etc. Cross-validation score, e.g., mean accuracy across different iterations. Visualization plots. Feature importance plot visualizes the importance of each feature in the final selected set. Feature selection path plot shows the selection process, including the features added or removed at each step. Fine-tune parameters. N features to select controls the number of features to be selected. Direction specifies the direction of feature selection, forward or backward. Scoring allows customization of the scoring function used for feature evaluation. CV enables control over the cross-validation strategy. Uncertainty methods. None. Sequential feature selector is a deterministic algorithm, so there is no inherent uncertainty in the selection process. Challenges and fixes. Challenge 1. Overfitting. When the dataset is small or noisy, the selection process might lead to overfitting. Sample use case. A dataset with a small number of samples and many features, where the scoring function is highly sensitive to noise. Fixes. Increase the number of folds in cross-validation. Use a regularization technique in the estimator, e.g., L1 or L2 regularization. Perform feature selection on a larger dataset or use techniques like bootstrapping to estimate the uncertainty. Challenge 2. Feature interaction. Sequential feature selector does not consider feature interactions, so it might miss important features that are only relevant in combination with other features. Sample use case. A dataset where the prediction is heavily influenced by the interaction of two features, but each feature individually has low predictive power. Fixes. Use a more complex feature selection method that considers feature interactions, such as recursive feature elimination with cross-validation RFECV, or a feature selection method based on a tree-based model. Create new features that capture the interaction between existing features. Challenge 3. Feature importance vs. feature selection. Sequential feature selector focuses on feature selection based on performance improvement, but it might not accurately reflect the true importance of features. Sample use case. A dataset where a feature is highly important but does not significantly improve the performance when added to the existing set of features. Fixes. Use other feature importance methods, e.g., permutation importance, SHAP values to complement the feature selection results. Consider using a feature selection method that is based on feature importance instead of performance improvement. sklearn features election RFE. Description. Recursive feature elimination RFE is a feature selection technique that works by recursively removing features and building a model on the remaining features. The goal is to identify the optimal set of features that minimize the model's error on a given dataset. Inputs. Estimator and estimator object, e.g., a classifier or regressor that will be used to fit the model during the feature elimination process. N features to select the number of features to select. Outputs. Ranking an array of integer values representing the ranking of features, where 1 indicates the most important feature. Support an array of Boolean values indicating which features were selected. Steps. 1. Initialize the model with all features. 2. Train the model on the entire dataset. 3. Remove the feature with the lowest importance score, e.g., based on feature coefficients in linear models. Feature importances in tree-based models. 4. Repeat steps 2 and 3 until the desired number of features is reached. Metrics. Accuracy. The accuracy of the model on a holdout dataset. F1 score, a metric that combines precision and recall. Useful for evaluating models with imbalanced datasets. AUC area under the curve, a metric used to evaluate the performance of binary classifiers. Representing the area under the ROC curve. Visualization plots. Feature importance plot, a bar chart showing the importance score of each feature. ROC curve, a plot that shows the true positive rate against the false positive rate for different thresholds. Fine-tune parameters. N features to select the number of features to select. Step the number of features to remove at each iteration. Verbose controls the verbosity of the output. Uncertainty methods. Cross-validation, repeatedly splitting the data into training and test sets to estimate the models. Performance on unseen data. Bootstrap aggregating, bagging, creating multiple models by randomly sampling the data with replacement to estimate the variance of the model's predictions. Challenges and fixes. Challenge 1. RFE can be computationally expensive, especially for large datasets with many features. Sample use case that resulted in Challenge 1 using RFE on a dataset with millions of features can take a long time to complete. Fixes to Challenge 1. Reduce the number of features before applying RFE by using other feature selection methods. Use a more efficient estimator, e.g., linear models are often faster than tree-based models. Challenge 2. RFE may not always identify the most important features, especially if the feature importance scores are not highly correlated with the model's performance. Sample use case that resulted in Challenge 2. A dataset with a strong correlation between features might lead RFE to select a redundant feature instead of the most important one. Fixes to Challenge 2. Try different estimators and compare the feature ranking results. Evaluate the model's performance on a holdout dataset to assess the usefulness of the selected features. sklearn, features election, RFECV. Description. RFECV, recursive feature elimination with cross-validation, is a feature selection method in scikit-learn that aims to identify the optimal set of features by recursively eliminating features and evaluating performance using cross-validation. It uses a Bayes estimator, typically a machine learning model like a random forest or logistic regression, to train and evaluate models on subsets of features. Inputs. Estimator. The Bayes estimator used for feature ranking and model training. This can be any estimator with a fit method that supports feature importance attributes or methods. Popular choices include random forest classifier, or random forest regressor, and logistic regression. Logistic regression. Step the number of features to eliminate at each step. A higher step value leads to faster processing but may miss optimal feature combinations. CV. The cross-validation strategy used to evaluate model performance on different feature subsets. It can be an integer specifying the number of folds or a cross-validation object like stratified k-fold or k-fold. Scoring, the evaluation metric used to assess model performance on each feature subset. This can be a string representing a predefined metric like accuracy or F1 macro, or a custom scoring function. Outputs support a Boolean array indicating whether each feature is selected true or eliminated false in the final feature subset. Ranking, an array containing the rank of each feature, with 1 indicating the most important feature and high values representing less important features. Grid scores, a list containing the scores obtained for each feature subset during cross-validation. This information can be used to visualize the relationship between the number of features and model performance. Steps. Feature ranking, the base estimator is trained on the full feature set, and feature importance scores are obtained using the estimator's attribute, e.g. feature importances for random forests. Feature elimination, starting with the full feature set. A specified number of features determined by the step parameter with the lowest importance scores are eliminated. Cross-validation, the remaining features are used to train and evaluate the base estimator using cross-validation. The scoring metric is used to assess model performance on each feature subset. Iteration steps 2 and 3 are repeated recursively until a predefined stopping criterion is met. For example, the process may continue until the model performance starts to degrade significantly. Metrics. Model performance, the scoring metric used for cross-validation. This metric reflects the performance of the base estimator on different feature subsets. Number of features, the number of selected features in each iteration. This information can be used to analyze the trade-off between model performance and complexity. Visualization plots. Feature importance plot, a bar chart that visually represents the importance scores of each feature. This plot can be used to identify the most significant features. Cross-validation plot, a line plot that shows the model performance measured by the scoring metric as a function of the number of features. This plot helps visualize the relationship between feature reduction and model performance. Fine-tune parameters. Estimator, choosing an appropriate base estimator is crucial for accurate feature ranking and model performance. The step parameter determines the number of features eliminated at each iteration. A higher step value may lead to faster processing but may miss optimal feature combinations. CV, the cross-validation strategy helps assess model performance on different feature subsets. Using an appropriate cross-validation technique can improve robustness and avoid overfitting. Scoring, the scoring metric is used to evaluate model performance. Choosing a relevant metric is critical for selecting the best feature subset based on the desired outcome. Uncertainty methods. Confidence intervals, calculating confidence intervals for the model performance on different feature subsets can provide a better understanding of the variability and uncertainty associated with the results.